everybody. Today we're going to be talking about kinetic molecular theory and the beginning of our gas laws. So this unit is all about gases, and the kinetic molecular theory is all about the behavior of gases. Kinetic means movement, so we're looking at the behavior and how gases are actually moving. Now, before we jump into the math and the gas laws, we're going to take a quick look at 5 assumptions that we make based on that kinetic molecular theory makes for ideal gases, and I have that here. This isn't necessarily how all gases behave all the time, but majority of gases under the right conditions will behave according to these assumptions at a variety of temperature and pressures. So our calculations that we'll do later, although not entirely precise or accurate, will be close enough to experimental values. So the first assumption that the kinetic molecular theory makes is that gases consist of tiny spherical particles. Now, remember back to S&P orbitals, we're talking about just spherical, tiny particles, and that they're identical for any gas sample. Now, we know that's not necessarily true. Oxygen particles look different than nitrogen gas particles, right? Again, this is for ideal gases. The second assumption is that gas particles have negligible volume compared to the volume of their container. Move that over a little. Because they're so tiny and because there's so much space in between them, we call that negligible volume. And that's why they can be compressed easily, because there is so much space between them that they can be compressed into a smaller space. The third assumption is that gas particles are in constant motion, in random motion, and always moving in a straight line. They will move this way until they collide with each other or with the walls of their container. Now, when these collisions happen, as you can imagine, there's some amount of force involved in that, and that force is what we refer to as pressure. So these collisions cause pressure that gases exert. So the more collisions that happen, the more pressure exerted by a gas. Now, because we're going to be doing calculations involving gas pressure, I do have the gas pressure units up here. Now, remember back to our equivalency statement. This is very similar to that equivalency statement for mole conversions. Each of these values equal to each other. The only difference is we're measuring in different units. So the units that we use in chemistry often to measure pressure is atmosphere, millimeters of mercury, torr, and kilopascals, abbreviated KPa. So this is our equivalency statement. 1 atmosphere of pressure is equal to 760 millimeters of mercury, or torr, and is also equal to 101.3 kPa. Now, the fourth assumption that kinetic molecular theory makes is that gas particles do not attract or repel each other at all. Again, this is for ideal gases. Not all gases are behaving this way all the time. Real gases, not necessarily. But because there are no or limited attraction or repulsions, gases will actually expand to fill their containers, take up as much space as possible. Now, the last assumption is that gases are perfectly elastic. Now, what this refers to is the collisions that I was talking to up here. When the gas particles are colliding, the pressure is going up, but the faster that they're moving too, the more kinetic energy they have. So perfectly elastic means that when they collide, that kinetic energy is not lost. All of it is either transferred to another particle or maintained within that particle. Okay, so none of that energy is lost. Now, the last thing that I want to note here is, because we're talking about kinetic energy, is temperature. Now, you may think of temperature as being how hot or cold something is, but in chemistry, temperature is a measure of the average kinetic energy of particles. Remember that kinetics is all about movement. So the faster particles are moving, the higher that temperature. The slower the particles move, the lower the temperature. Okay, so we're actually looking at how fast and how slow these particles are moving. When we get to doing our calculations for the gas laws, we need to make sure that we're always using temperatures in Kelvin. Now, typically you're going to be given temperatures in degrees Celsius, but we have to convert that to Kelvin using this simple conversion. Kelvin is equal to the degrees Celsius plus 273.1. Now remember, for all the gas laws, we want to make sure that we are keeping those in Kelvin.
Okay, so now that you've learned a little bit about the kinetic molecular theory, I'm going to talk to you about some of the gas laws. Gas laws are basically formulas that we use to solve word problems in chemistry class. And today we're going to be learning about 4 of them. Our first one is Boyle's law. And Boyle's law represents the relationship between pressure and volume of a gas. And this relationship is actually inverse, meaning that pressure and volume are inversely related. That is represented as the formula initial pressure times initial volume equals final pressure times final volume. Now you can see that we have little subscripts 1 and 2, and that represents 1 represents what we start out with in the beginning, 2 is our variables at the end. So as you can see in this, temperature is not included, which means it is constant throughout the reaction or experiment that is happening. So meaning they're inversely related, that means that as pressure increases, volume is actually going to decrease. And then as pressure decreases, volume increases. You have experienced this probably when you've been on an airplane. As we go up into the atmosphere, there's less pressure pushing on the outside of a water bottle, and then therefore the volume of the gas inside of that water bottle is going to expand. And I know that I'm sure some of you have witnessed people spilling water all over themselves because that gas is expanded because there's less pressure. So this relationship actually looks like this on our graph. The second law is Charles's law, and it shows the relationship between volume and temperature when pressure is constant. Note, pressure is not in this equation, or in this formula. So this is actually a direct relationship between volume and temperature. And so we have our initial volume divided by our initial temperature equal to our final volume divided by our final temperature. So the direct relationship tells us that as temperature increases, volume also increases, or as temperature decreases, volume decreases. This has to do with what Ms. Frankovic was talking about related to the kinetic molecular theory. As temperature increases, our particles are moving more quickly and they get farther apart. And then if temperature is decreasing, they're actually going to slow down and not be as far apart, so therefore the volume decreases. This relationship looks like this. It can go in either direction, I guess. Okay. Our third is Gay-Lussac's law, and this is representing the relationship between pressure and temperature, which again is directly related, and in this volume is constant. Therefore, we have initial pressure divided by initial temperature, which is equal to final pressure divided by final temperature. Like I said, this is a direct relationship. Therefore, if temperature increases, so does pressure. Or if temperature decreases, so does pressure. Again, this relates to the kinetic molecular theories, the assumptions that we've made on the last board, because as temperature increases, our particles are moving more quickly and they're hitting the sides of our containers, and which means that the rate at which they're hitting the sides of the containers and with the force, that is the measure of pressure. So they're going to move more quickly, hit the side of the container more, pressure is higher. When temperature decreases, that is the case. This relationship looks just like this one. Our combined gas law is actually a combination of all 3 of these. And as you can see, it includes all 3 of our variables. So we have pressure, initial pressure times initial volume divided by initial temperature, which is equal to our final pressure times final volume divided by our final temperature. You can see that no variables are held constant here, and when we practice identifying which law to use, you are going to see that is your big key for this one. If we have all our variables and none of them are held constant. Now we're going to do some practice problems, some examples related to this. Like I said, the difficult part for us at the beginning is identifying all of our variables. So our first example is that we have 1 liter of hydrogen gas at 25 degrees Celsius, which increased the temperature to 50 degrees Celsius. What is the new volume? So I like to make a variable list, and that's what I like you guys to do in class. So we're going to start with this. Our initial volume is 1.00 liters of hydrogen gas. I should put that. Our initial temperature is 25 degrees Celsius, but we need to convert that to Kelvin.
Notice that there's no decimal place because 25 degrees C has no decimal place.
And when we're adding and subtracting, least known decimal place determines sig figs. So our final temperature was 50 degrees Celsius. Again, converted that to Kelvin. And it asks, what is the new volume? Now, if I look and see here, I have volume and temperature, and I look to see which of my laws represents that, I see it is Charles's law. So Charles's law shows us the relationship between temperature and volume. So I write down my formula that I'm using, I plug in all my units, or all my givens, and what I end up doing is I'm cross-multiplying here. So I end up with my final volume times 298 Kelvin equals my other two values. I divide by 298 Kelvin on both sides. And my final volume, 1.08 liters, making sure that I have my correct number of sig figs. I'm good.
And you can see that Kelvin on both sides is crossing out. So the only unit that you're left with there is going to be liters.
Oh yeah, sorry. My bad. Yeah, my Kelvins cancel out.
Now, another way to look at the problems is to actually label your variables while you're reading the problem. So, I have 1 liter of hydrogen gas at 25 degrees C and 5 kPa. So I'm going to label this 1 liter. Here's my first volume. 25 degrees C I see as a temperature. We're going to see that that one's actually not important here. And I have a pressure, an initial pressure of 5 kPa. It decreases, the volume decreases to 0.5 liters. So here's my new volume, my V2. What is the new H2 pressure? Okay, so here I'm looking for P2. Now notice that temperature is not mentioned again. This is just saying that temperature is constant at 25 degrees C. Okay, so we're going to use an equation that does not involve temperature. Which equation does not involve temperature? P1 V1 equals P1 V1 equals P2 V2. Okay, this is Boyle's law. Now, what do we have here? We can plug it in, right? We should add these in. 5 kPa, our variables list. Volume 1 is 1 liter. Our P2 is unknown, and our V2 is 0.5 liters. Okay, now I can plug this into my equation. So P1, 5 kPa, times V1, 1 liter, is equal to P2, which we don't know, times V2, which is 0.500 liters. Now, in order to isolate my P variable here, I'm going to have to divide both sides by this 0.500 liters. So it crosses off here. I'm going to divide the left side by 0.500 liters as well. My liters cross off, and I'm left with 5 times 1 divided by 0.5, which is 10.0. My last unit that I haven't crossed off here is kPa. So the new pressure after the volume decreases is 10 kilopascals. Now, the last one that we have here is taking a look at what formula we're going to use for a longer problem. We're going to label this as we go. So a 35...
We recommend that you pause here and you try and label all the variables and then rewatch everything. Okay.
So a 35 milliliter gas sample, that's a volume 1, at 15 degrees C, here's a temperature, and a pressure of 96.7 torr. There's an initial pressure. Expands to a volume of 8 liters. Okay, that's a new volume. The final pressure of the gas is 50.7 torr. That's a new pressure. What is the final temperature? So we're looking for a T2 in degrees C. Now notice, we have a V1, a T1, a P1, a V2, a P2, and we're looking for T2. What formula, what law are we going to use here? We're going to use the combined gas law, right? Nothing is being held constant here. Okay, so we need the law that shows nothing's being held constant. P1 times V1 over T1 is equal to P2 times V2 over T2, right? That's it.